So the regression line here is shown, and in particular the values yi hat on the regression line, and the MSS is the sum of squares, the model sum of squares, the sum of distances from the yi hat to y bar squared. And so you can see that when MSS is small, that means that the regression line is horizontal. In fact, it's y bar, and so beta 1 will be small, the slope. If MSS is large, then beta 1 will be large. So we can use this to define a F statistic. So we have F1 n minus 1 minus 1. So this is a F statistic, and this is MSS over RSS over n minus 1 minus 1. So the null here is that beta 1 is 0, and the alternative is that beta 1 is not 0, and we reject if F is large, in other words, if MSS is large. R squared is called the coefficient of determination. It is MSS over TSS, and it's the fraction of the total variability of y1 to yn explained by the variance of y1 hat to yn hat. So today we're going to cover multiple linear regression. Multiple linear regression generalizes simple linear regression to having more predictors. The standard statistical model y is x beta plus e, where y is a row matrix here. I'm sorry, a column matrix. And E is E1 to En. X is our design matrix. It's an n by k plus 1, and beta is a k plus 1 by 1, and that's our Tyche constants. So the assumptions in our model is that the xij's are fixed numbers. The x has full rank, in other words, independent columns, so that we can find beta hat. So having x full rank means that x transpose x is invertible, which is important, so we can find beta hat. E1 to En are IID normal 0 sigma squared. We need normality so that beta hat is a normal vector, which is important if you want to do hypothesis testing. EI are homoscedastic, and this is so that you can find the variance of beta hat. So we showed that y hat is x beta hat defines a regression plane where beta hat is x transpose x inverse x transpose y. So recall that beta hat was defined as the beta which minimizes the Euclidean norm. And in fact, beta hat is the argmin of y minus x beta. So beta here is our variable, and beta is in rk plus 1. We have, actually, yeah, so beta 0, beta 1 up to beta k. Those are all parameters that you can use to minimize the Euclidean norm squared. Okay, so here is the picture of the regression plane. Say if we have two predictors, then our regression line becomes a plane. We have x1 and x2. The mean is now a plane. The mean of y is now a plane. And this picture shows the distances, the regression, the residual, the model distance, as well as the total distance, just as before. So we have TSS is MSS RSS, just as before. TSS has n minus 1 degrees of freedom as before, but the MSS now has k degrees of freedom, and the RSS has n minus k minus 1 degrees of freedom. R squared is MSS over TSS, coefficient of determination, and Fk n minus k minus 1 is this ratio here, which if you do some algebra, you can write it in terms of R squared. And that is helpful to know. So facts from Theorem AB on page 573, 575, 774 is that the beta hat is an unbiased estimator, and its variance is given by sigma squared x transpose x inverse. So this is the variance covariance matrix. In lecture 4, we showed that sigma squared hat is RSS over n minus 2, is an unbiased estimator of sigma squared. Now we have that R squared hat is RSS over n minus k minus 1 is an unbiased estimator of sigma squared, because k now is no longer 1 necessarily. So we can do an F-test whether beta 1, beta 2 up to beta k are all 0. For simple linear regression, we only have beta 1, and F is equivalent to a t-test, as mentioned before. So if we reject the null, it's only natural. My handwriting's getting worse and worse. Sorry about this. To ask which of the beta I are statistically different from 0. In other words, which of the variables x1 to xk have a relationship with y. So as mentioned above, the variance of beta hat is sigma squared hat x transpose x inverse, where sigma squared hat is RSS over n minus k minus 1. In particular, the standard error squared. So the standard error squared is the II entry, is the II element of this variance covariance matrix. And so I'm borrowing a fact from Glantz's applied and regression. Sorry, it's Glantz's applied regression and ANOVA book. That this is sigma squared hat over n variance xi 1 minus xi squared, where here xi squared is the r squared obtained by regressing xi on x1 up to xi minus 1, skipping xi plus 1 up to xk. So you just treat your xi as your response variable y, and you're regressing on these k minus 1 variables here, and you'll get then an r squared, which is your MSS over TSS, and so that is your RI squared. So just as some examples here, if k is 1, then if k is 1, then R1 squared would be 0, since there's no other predictors than x1. So in this case, the sample variance would be sigma squared hat over n variance of x, because 1 minus r squared is 1, and that's exactly what we got before. If k is 2, then R1, 2 is just the correlation coefficient squared between correlation of x1 and x2. So it follows that if the xi are correlated with other predictors, then 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 the standard error squared will be large. And that's because this 1 minus Ri squared term will be small, and it's in the denominator, so that'll make the standard error squared large. And if the standard error is large, that means you have huge confidence intervals. And furthermore, since the standard error is in the denominator of the t-statistic, it'll mean that your t-statistic will be very small, and it'll be very difficult to reject the null. So this will make the t-test for the null that beta I is 0 be useless. So this is called multicollinearity. So to recap that, if you have multicollinearity, you have some correlation between your predictors. What that means is that you may end up rejecting the null according to the F statistic, but the F statistic won't tell you which of the beta I's are statistically greater than 0. And so you would do then individual t-tests as you did in ANOVA, but the t-tests are going to be inconclusive, right? Because the standard error are going to be so large that you won't be able to reject any of the nulls. So your F test will say reject the null, but all the t-tests will say that you can't reject a null. So next, it's important to understand that R squared can only increase by adding more predictors. So R squared is 1 minus RSS over TSS. Now TSS is the variance of the y, and this is fixed when you take your sample y1 to yn. So let's argue that going from one predictor to two predictors decreases the RSS and hence increases R squared. So RSS, right, it's the min arg over beta 0 in R, beta 1 in R of the sum of the residuals here. So you're looking for the beta 0, beta 1 that makes this as small as possible. Now, so you find the beta 0, beta 1 that makes it as small as possible. You call beta 0 hat, beta 1 hat. Now, if you add a predictor, now your RSS is the min arg over 3 parameters. And this sum is at least as small as the RSS with one predictor, since you can just make beta 0 and beta 1 the same as before and beta 2 be 0, and then the RSS will be equal. So you might be able to make it smaller with another choice of beta 0, beta 1, beta 2. So adding a predictor increases R squared, and the F test also will increase because as R squared gets larger, the numerator gets larger and the denominator gets smaller. So we introduce the R squared adjusted, which is defined as 1 minus RSS over n minus k minus 1 over TSS over n minus 1. And this is a way of penalizing having too many predictors. So if you do some algebra manipulation here, you get 1 minus n minus 1 over n minus k minus 1 times RSS over TSS, and that is less than 1 minus RSS over TSS, which is R squared. So R squared adjusted is smaller than R squared. It deflates R squared when you add additional parameters, since it becomes less for increasing k. So as I mentioned, we've gone through the theory now. In lab, you'll be practicing these ideas, and in lecture on Monday, we'll also do some examples. So it'll just cement everything for you. Have a great weekend. Bye-bye.